Guys, welcome to my YouTube channel. Today I'm going to talk about conversion factors. That's what we're going to discuss today. So we talked about a little about dimensions, the lengths, and we talked about the numbers in chemistry that are really small. So what I'm going to do today, right now, is to first start with the conversion factors of the temperature. Okay, there are three scales for measuring temperature. Those are degree centigrade, degree Fahrenheit, and Kelvin. For Kelvin, there's no notation of the Kelvin degree for Kelvin, and we don't also talk about that. Okay, so let's just talk about how do you convert centigrade to Kelvin. So Kelvin is obtained. I'm going to just write down real quick those centigrade minus 273, that's the conversion. And if you do want to do reverse degree centigrade, then simply becomes, you could just move this 273 to the other side, and it's a subtraction addition, so this minus becomes plus. And that's always happens when you want to do subtraction additions. For the centigrade to Fahrenheit, if you want to focus on that, from centigrade to Fahrenheit, degree Fahrenheit would then be 1.8 times degree centigrade plus 32. And if you want to reverse that, then you have to move this 32 to the other side. That becomes Fahrenheit minus 32. And then degree centigrade then becomes this number divided by 1.8. So these are the conversion factors. You don't really have to memorize those, but you should be able to use them. Okay, so what I'm going to do here is quickly going to do some conversion that I think is useful. Liquid nitrogen is a familiar that some of you may have heard of. It's a very, very cold stuff that if you actually wants to have a temperature that is so cold, that's what you're going to use. Okay, so let's talk about liquid nitrogen and its uses. And we do know that liquid nitrogen boils at 1 minus 196 point, my bad, negative 196 degrees centigrade. So let's convert this to Kelvin to see how Kelvin works, and that's the Kelvin is whatever centigrade you have plus 273. Okay, so that's what we just wrote down, and we do this plus 273, and it gives me 77 Kelvin. Again, there's no degree Kelvin here. Okay, so it could be that there is this Kelvin thing that is actually doing that. So by going to that, we could actually see that. Let me just fix this real quick. Okay, so we're gonna have this on our background going forward, and we could see that liquid nitrogen, how we go from degree centigrades to Kelvin. Let's do one more useful conversion, or maybe two. What is 0 degrees centigrade in Fahrenheit? Okay, in degree Fahrenheit. How do I do that? Let's just quickly go to 0 degrees centigrade, and I want to find out what my Fahrenheit is. So the relationship is then my Fahrenheit should be 1.8 times 0, which is my degree centigrade, plus 32. So that would be 32 degree Fahrenheit. 0 degrees Celsius. And let's just see what 0 degree Fahrenheit would be in degree centigrade, and the relationship for that, like converting 0 Fahrenheit to degree centigrades. I do have that degree centigrade is my Fahrenheit, which is 0 minus 32 divided by 1.8, and if I do that, we would find that it's minus 17.8 degrees centigrade. So that's how that works. Okay, so if you have 0 Fahrenheit, that would be how you do that. You do Fahrenheit minus 32, which gives you a negative number, then divided by this to give you that number that is degrees centigrade. So 0 degree Fahrenheit would just be minus 20 or about minus 20 centigrade, and 0 centigrade would be about 32 degree Fahrenheit. So that's how it works, and it's really that simple. You have to work with it to actually know the hang of it, really. So that's not a big deal. I also want to go on to the conversion factors where we have the density and play with that a little quick. But before that, I want to talk about dimension and lengths. So we talked about small things like a molecule, a benzene molecule that is something like 3 times 10 to the minus 10 meters. A buckyball that is kind of 25 10 to the minus 10 meters. A virus, which is kind of like a little bigger than the buckyball, actually a lot bigger than the buckyball, and it's something like 500 nanometers or 10 to the minus 9 meters. So the whole point is here, instead of this we say 3 angstrom, that is equivalent to angstrom. This we also demonstrate in angstrom, and for this we could just say 500 nanometers, that is more useful than 10 to the negative 9. And that's the whole point. For E. coli, the bacteria, the dimension is something like 2000 nanometers, so 4 times bigger than a virus, and red blood cell that is kind of 7000 nanometers. So that's how small these things are. So we have to use something like an angstrom or nanometers that we could actually talk about a small, not only molecules but also small biochemical entities like cells or viruses or those kind of things, bacteria, those kind of things. Okay, so what if I want to convert 10 to the minus 10 meters, which is an angstrom, to meter? Well, that's simple. I just have this conversion factor and I can do that. But what if I want to do, like if somebody told you that it's 200 angstroms, how are you going to express it in meters? Then you have to just replace the angstrom with its equivalent in meters, and that would be 200 times 10 to the minus 10 meters. And you could make it simple, then 2 times 10 to the, so 200 and times that, it would make this bigger a little bit, and minus 8 meters. Just like we discussed, if you make this 200 small, you have to make that one bigger by 2 orders. Okay, now what if I want to convert this much cubic angstrom to cubic meters? Then what do I have to do? Then the conversion factor simply wouldn't be like this. Okay, and I have to have a conversion factor that goes from cubic angstrom to cubic meters, so that I could replace, instead of my cubic angstrom, something that is in cubic meters. So I could get both parts and raise it to the power of 3. This part raised to the power of 3 would be angstrom cubed, and this part to the power of 3 would be meter cubed. But this thing to the power of 3, it would be 10 to the minus 10 to the 3, which we could do let's just have it here, 10 to the minus 10 to the 3. We could have it on a a trick or a kind of a real quick mode to do it, but I'm going to show you how we do it in a language that everybody understands what we're doing, and then we do the trick. Okay, that's always a better choice. First you understand what you do, and then you do the trick. So the best thing is to actually multiply it 3 times. That's the meaning of anything to the power of 3. And then once we have that, we could actually add those powers, and that's minus 30. Minus 10, minus 10, minus 10, that's minus 30. Okay, so this would be minus 30. How else do I know that? If you just do this to the power of 3, something to the power of something to the power of something else, it would be these two powers multiplied by one another. So that's the 3. So minus 10 times 3 would be minus 30. So that's the quick way of doing this. Okay, so that would be let me see if you all could see this. So I just move this. 10 to the minus 30 cubic meters is that much cubic angstrom. So if I want to use that, I use the same conversion factor to do this. Let's just try to use that conversion factor. So we find out that 10 to the minus 30 cubic meters is just 1 cubic angstrom. So I just replace that instead of that, and that would be 200 times 10 to the, instead of this cubic angstrom that you have here, I'm going to use its equivalent, cubic meters. And then you could make it also simpler, 2 times 10 to the minus 28 cubic meters. 200 cubic angstroms. Okay, so that's how we do this. Also, if you want to do the reverse, you could just make this 10 to the power thing to the other side, and if you do that, because it's multiplied, it goes down, and it should be 1 divided by 10 to the minus 30. And when you do that, you have to change the sign. It's 10 to the power 1 is equal to 10 to the power of 0. So 0 minus minus 30, that makes 10 to the 30. Okay, so that becomes 10 to the 30. Like, you could also have another conversion factor, that is cubic meter is 10 to the 30 cubic angstrom. So if you just want the reverse thing, you could just move the 10 to the power of thing to the other part, and that would be just change sign. Okay, go from anything that is minus to anything that is to the same thing that would be plus. So that's how you do this, and it's important. We will also do it for square meters to square centimeters, or square usually a smaller numbers like a square micrometers, those kind of things. Okay, and micro, by the way, is this. That is the sign that you use for micro. That's what you do for micro. Okay, so that's also about that. Let's move on to, we did this, to the density. Now density is d equal m over v. D here is my density, that is in gram per milliliter, or in gram per cubic centimeters. My volume is in milliliters or cubic centimeters, based on which density I want, and my mass is usually in grams. It could also be kilogram over liters, or kilogram over actually kilogram over cubic meters. It could be the same. It could be all those dimensions as well. So the point about density is that there are 3 formulas actually that you need to know about density. If you solve it for the density, that's the root formula that you know, D equals m over v. If you want to solve for volume, that would be volume. Now I put my volume to the other side, it comes to the top, because it's multiplication and division thing. So anything from the below, if you move it to the other side, it comes to the top. Anything in the top, if you move it to the other side, it goes down. So volume would then be mass divided by density. And if you solve it for m, so here we have solved it for d, if you're interested in d and you've been given these two. If somebody gave you mass and density and you're interested in volume, you're going to use that. And you could also solve it for mass, and that would be moving volume here to the other side, and that makes d times v, or moving d to the other side here, that also makes v times d. That is, mass is density times volume. So that's how we use the formula for density. I'm interested to do two examples of density. Pumice is a volcanic rock. Let's say a problem tells you that 153 sample of your pumice, 155 gram sample of your pumice, which is a volcanic rock, occupies this much volume. And pumice is very lightweight because there are, in the process of the volcanic eruption, there's many air bubbles trapped in this kind of rock. So that's why it's very lightweighted. And if you do so, you would find that this is your mass and this is your volume. So, my bad. Volume. So the density would then be your mass over your volume, 155 divided by 163, and it would be gram per milliliters, because this is in grams, this is in milliliters, gram per milliliters, and the answer would then be, let me just check, 0.95 gram per milliliters. Then the question also asks if it's going to float on water. The density of water, by the way, D of H2O liquid, is 1.00 gram per milliliter. So this is definitely going to float on water. Also, the density of ice, we all know that ice floats on water. Density of H2O solid, and this that I do in parentheses, H2O stands for water, and the same thing if you do liquid, it means water, and if you do S, which stands for solid, it means ice. So that's the language of chemistry as well. So H2O is the formula, and liquid, it means liquid water, and solid in parentheses means the state, the physical state. And there are three states. There's the gaseous state that we do parentheses gas, there's liquid that we do like this, and there's a solid that we do like this. So the density of solid water or ice is 0.92 gram per milliliters, and you could also see that this one also floats on water because it has less density. It's less denser than water, so it kind of floats on water. What about pumice? Like if you put it in a container that contains alcohol, and somebody gave you that the density of your alcohol is density of ethanol is going to be 0.789. Now you could see also gram per milliliters. Now you can see that both your pumice, that was what we get for pumice, both pumice and ice are going to actually sink in ethanol, because the ethanol has less density, so they would sink in. So that's this problem. And also I'm interested to know to do one more problem on density before I move on and wrap this video up. There is this question that says a neutron star has a huge density of 9 times 10 to the 7 gram per milliliters. What would be the weight of a teaspoon of this? Now these neutron stars are big condensed star that we don't find anywhere on Earth. The densest metal, like Au for example, gold, is something like 20 gram per milliliter. But this is like 9 times 10 to the 7 gram, even more than a billion gram per milliliters. So a teaspoon of that would weigh a huge amount of, like, that would be a tremendous weight that you can't believe it. I just want to try to do this. If we assume the teaspoon is 4.5 milliliters in volume, then let's see what a teaspoon of this neutron star, just that a small speck of that neutron star that you could actually put it in a teaspoon, it would weigh then. So this is the volume, that's the density, and mass then would be density times the volume, and that would be this times that. And let's see what do we get if you, here did a bad thing. That was 2 times 10 to the 7. Okay, so this times that, and my mass then would be, mass is 2 times 10 to the 7 times 4.5, and would be, this is mass times my density, and that's my volume. Density times volume gives my mass, and that's 9 10 to the 7 grams. I could convert it to kilograms, and that would be, because each kilogram is 10 to the 3 grams, so this would be 10 to the 4, 10 to the 3. I could actually wrote 10 to the 7 like this, grams, and then it would be, this thing would be kilogram. Also, I could write that as 10 to the 3 kilogram, and 10 to the kilogram, everybody knows it's like the ton, so it would be 9 times 10 tons. Okay, so my mass would then be 90 tons, and that's how big or how massive that the small teaspoon of a neutron star would be. Okay, but these things literally doesn't exist in anywhere near our planet or in our solar system. They're far, far away, and they're condensed matter, so they emit gamma rays. They are pulsing stars, and they are a very condensed phase of matter, very near to the state where you have the creation of a black hole. Okay, so they're very dense. So that's for this. And also I want to talk about one more thing that is very important, one more number that is important in chemistry. When you talk chemistry, you can't literally count molecules or ions or things like that. What you do, you have to actually go on and try to count them in a scale that is rational. Okay, so that's not how do we count them? Do we count like let's assume phosphorus molecules? Do we count one of them, thousands of them, billions of them, trillions of them? The answer is no. The only number that works in chemistry is the Avogadro number, and that's defined as 1 mole of a substance, and then 6.022 times to the 10 to the 23. So it's way much larger than a billion or a trillion of whatever number that you could think of. Okay, million being 10 to the 6, billion being 10 to the 9, and then trillion being 10 to the 12. That there's no match for this number that is 10 to the 23. Okay, so that's the Avogadro number. It means 1 mole of H2O, for example, it would have 6 times 10 to the 23 H2O molecules, and because each H2O now have 2 hydrogens, you could do 2 times 6 10 to the 23, and that would be 12 times 10 to the 23 H atoms. So we kind of work with this number, and later on I will do examples of this. But what is more important is that in chemistry we also have substances and we want to weigh them. Okay, so we weigh them and we measure them with mole. Each mole of any substance has a mass in grams, and this mass is a particular mass that chemists are interested, because every time we're interested in picking that exact 6 to the 10 to the 23 number of molecules, that would be the definite number of molecules or the subparticles of that substance that we're talking about. Okay, so this mass, we call it the molar mass, and because it's a definite mass of this much of particles that we call 1 mole, we're going to write it down like m. So m is the molar mass, and it's in the gram per moles, just like density we talked about. This thing is the molar mass, we define it as such, and molar mass is mass in grams divided by the number of moles. Okay, so this number of moles actually doesn't have any special dimension. We just use it as n, show it as n. Mass, we all know we show it as m. and a small m just like any mass, the mass of the substance that we just weighed on a scale. And if we do divide our mass by the number of moles, we get the molar mass. Okay, so just like density, it's important to be able to rearrange this. So if we're interested in the molar mass, we always have to divide our mass by the number of moles. If we could solve it for m is n times the molar mass, number of moles times the molar mass would give you the mass. Like if somebody told you half mole of water, and molar mass for water is 18 gram per mole, you just do this times that, and that will be 9 gram of H2O. Like half mole of H2O would be just 9 gram based on the formula that I just showed you. You could also solve that for N, and N then becomes mass divided by the molar mass. It gives you the number of moles. So all three versions of it you should be able to actually rearrange and work with. That is also important in chemistry. And let's see if I wanted to talk about anything else in the conversion factors that are important. I believe that is all, and I'm going to wrap up here, and we will talk later on about how we do calculate the molar masses. Let me see if the video is lengthy enough, so we'll talk about any different chemicals. When we talk more about chemicals, we're going to get to understand how we find a molar mass for any a specific substance. Okay, thank you for watching, and let's wrap it up here.